In certain applications, we can be given a data set. And with a data set, what we'll have are X and Y values, which will create these ordered pairs. So like with this data down here, they collected the chirps per 15 seconds coming from crickets, as well as the temperature outside. So we have these ordered pairs, like this one would be when it was 66 degrees outside. They heard 33 cricket chirps within 15 seconds. Then when it was 72 degrees outside, they heard 35 chirps. So we end up with these ordered pairs. And what we want to do is graph this data to see if it creates a roughly linear model. So let's talk about making this graph, which will be called a scatter plot. And what we're going to do is we're going to use Desmos to help us out to create this graph for us, and then it's going to carry out some pretty heavy calculations for us as well. But let's just start with the graph. So what we're going to do is going to the Desmos graphing calculator, which I have on the right-hand side of my screen here. We're going to this upper left-hand corner where there's this little plus sign that adds an item. And we have these different options, and we want to add a table. So we have X1 and Y1, and we want to add our X values and our Y values, having them line up. So with our data set here, let's go ahead and call the cricket chirps X, and we'll call the temperature Y. And we'll plug this into our table here. So for cricket chirps, we have 45, 35, 20.4, 33, 31, 35, 18.5, 37, 26. And then in the next column, we want to put in the Y coordinate. So 80.5, 70.5, 57, 66, 68, and 72, 52, 73.5, 53. Okay, so we have all of our data input. It's always a good idea to read it over again and make sure it's all correct. And then let's go ahead and with our graph screen, we can find our data set. And this right here, it's a little jumbled, but it is roughly linear. We can kind of visualize a line that would go through this data. And while it won't go through every single coordinate, we call this the line of best fit because it's as close as it can possibly be to all of the data points at the same time. So what we can do is kind of visualize this line going through the data, and where this line will be beneficial is that then we can use that equation to make estimations. We can kind of predict what would happen. So even though we don't know what the temperature is when there are 30 cricket chirps, what we could do is use this line to estimate what's the temperature when we hear 30 cricket chirps in 15 seconds. So to get this equation of the line, we're going to jump down to step 3 up here, where we're going to add an expression into Desmos. So I'm going to go to this line 2 right here. And I want to write down Y1. So I'm going to go Y1. And just so you know, with the keyboard, I type in Y, I type in 1, it automatically adds it as a subscript there, so you don't have to do anything special with notation there. If you just type a Y and a 1 on your computer, it'll automatically put it down there. Then we're going to have our little squiggle symbol, which should be above the tab key on your keyboard. So I'm going to go shift and that key above tab. And then we're going to have M times X1, which again, just typing X and then 1, it automatically puts the notation in there, plus B. And what we can see is that Desmos has automatically graphed this line of best fit that goes through our data and fits our data as best as it can going right through it. And then with all of this information here, we're just going to go down to parameters where it tells us about slope and intercept. What this is doing is it's giving us an equation for this line of best fit. So what I could do is write down this equation that is y equals, so our slope M is going to be a 1.1432, and then times X plus B, which is 30.2806. And now what we have is an equation where we can make estimations of temperature, make estimations of chirps per 15 seconds, relating these two values. Something we want to keep in mind when we are making those predictions is the difference between interpolation and extrapolation. So if we look at our data set over here, we can see that we have data values ranging from, and let's look along the x-axis here, so like about 18 all the way up to, what is that, maybe 45-ish. So in terms of X values for the cricket chirps, we have an idea of what's happening between 18 and 45 cricket chirps. So with that, we know this line is estimating really well in there. We don't really know what's happening outside of there. It might be linear, maybe this model continues, but we'd want to be careful of going outside of our model. So for estimating with X values outside, like say we hear 60 cricket chirps in 15 seconds, we want to be careful of using this as our estimate because maybe on this higher end, there's a completely different model. So we can use it to extrapolate, but we just want to be very careful. So let's get some definitions and write some things down. So interpolation is making estimates within the model, or let's say making predictions. That's what we're doing within the data set. And then extrapolation is making predictions outside of the data set. And with these, we want to be careful. So if you extrapolate, you can do it, but be careful. And sometimes the answer just won't even make sense when you do that. So sometimes it's really obvious, sometimes it's not so obvious. Okay, so would predicting the temperature when crickets are chirping 30 times in 15 seconds be interpolation or extrapolation? So what I'm doing is I'm looking at this x equals 30, and I'm seeing if it's within our data set, which, like I was saying, we have this lowest value. Here we can actually see lowest value of 18.5, largest value of 44. So because 30 is between those two values, this would be interpolation, which we can trust our predictions with interpolation. So make the prediction and discuss if it's reasonable. So to make the prediction, what we're going to do is plug in x equals 30. So I'm going to have y equals 1.1432 times 30 plus 30.280. So with that, let's go back to our calculator. And let me kind of move my screens around. All right. So 1.1432 times 30 plus 30.2806 for 64.5766. Let's go ahead. It looks like they're rounding to one decimal place up above, so let's do the same thing. So when there are 30 cricket chirps, we estimate that it is about 64.6 degrees Fahrenheit outside. And you know what? That fits our model pretty nicely. 30 is landing in between there, and the 64.6 is landing between there. And then in terms of our graph, what this is translating to is that we're plugging in, let's see if I can move out here. We're plugging in 30. So it's like we're plugging in this value of 30 and it's giving us the output along this line, which is the 64.6. All right. Would predicting the number of cricket chirps of chirps the crickets will make at 40 degrees be interpolation or extrapolation? So pay attention to this one is actually talking about giving us a temperature. So let's take a look at what our lowest temperature is and what our highest temperature is. So we have a lowest temperature of 52 and a highest temperature of 80.5. So 40 is outside of that range there. So with that, this would be extrapolation. So this one is telling us y is equal to 40, and this would be extrapolation. So with this, we can plug in, and in this case, it would be that we would be going 40 equals 1.1432 times x plus 30.2806, and then we would be solving for x. And when we get our result, we'll just have to see if it's reasonable or not. And from there, we would just want to have in our statement that we want to be careful because we are going outside of the data set. So let's see, we have 40, we're going to take away 30.2806, and then we're going to take that result and divide it by 1.1432 for 8.5. Chirps in 15 seconds. So, pretty slow chirping from the crickets, but it is colder outside. It's not totally unreasonable, but we'd want to be careful. It's getting to a point where we're kind of verging on 0 cricket chirps, and maybe that is a case, but seems somewhat reasonable. But we would just want to be wary that we are in fact extrapolating from our data. So we would probably want to gather data that would look at more colder temperatures and see the results to see if we do in fact have a linear model there, and if it's a continuation of this model or a separate linear model. Okay, let's look at one more example here, just kind of a fresh start to go through that process again. So we have some data here, and we have these years and gasoline consumption from 1994 to 2004. Determine if the trend is linear, and if so, find a model for the data and use the model to predict what's going to happen in 2008. So we are going to be extrapolating here because we're going outside of the model. We're not going too far outside of the model, so we should be okay, but we just want to keep that in mind. Okay, so I'm going to add a table, and we're going to use the years 94, 95, 96, 97, 97, 98, 99, and that's not going to work. How about I'm going to change this to years after 1990. So I'm going to go 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, because I couldn't put in just 0 there, so you can change the units however you need to. You just have to be consistent. So maybe I'll even make a note to myself that X I changed to number of years after 1990. So I changed that to a 4, 5, 6, 7, so on and so forth. Okay, then gasoline consumption in billions of gallons. We have 113, 16, 18, 19, 123, 125. All right. Whew. That looks very linear like that. That is very linear data. Again, it's a little squiggly, but that's because of just randomness. But overall, it's kind of like if we step back from it, it looks very nice and linear. Okay, so with that, then I'm going to get my line to estimate. So I'm going to go y1, squiggle, mx1 plus b. And then with that, we grab our parameters. So I'm going to have y equals, let's see, a slope of 2.2091 times x plus 104.482. And we're going to use that to estimate what's happening in 2008. So what we're going to do is with 2008, we're going to let x equal 18. and plug that in. So I'll go to my scientific calculator and do 2.2091 times 18 plus 104.482 to get 144.25. And this will be in billions of gallons. And I would just want to make a note to myself that this is extrapolation. So I just want to be wary of this answer, that it is going beyond the data set. But we have a pretty strong data set there, and it looked very linear, that I would be shocked if that trend didn't continue. Although we could start reflecting on world events in that time, and the recession was coming, all sorts of things. But we go ahead and trust that answer. Just make a mental note of extrapolation. All right, so that is making a linear model to fit data sets. And with that, we really are going to just focus on using the Desmos graphing calculator. Out there, there are calculations to find slope and to find the y-intercept, but we're just going to focus on using technology to get there.